All right, we're told to identify all of the real and imaginary roots, or zeros, of the function g of x. So pause this video, have a go at this, and I'll give you a hint. The rational root theorem will be useful. Okay, now let's think about what the rational root theorem tells us. It tells us if this polynomial here does have rational roots, it can be made up based on the factors of the constant term, and we could call the constant term right over here p, and the factors of the coefficient on the highest degree term, which is also 3. Let's call that q. So let's think about the factors of p. So I'm going to list p factors right over here, and we want the plus or minus version of it. Well, luckily 3 is a prime number, so it only has 2 factors. So we could have a positive 1, we could have a negative 1, we could have a positive 3, or we could have a negative 3. And similarly, q is also a 3, so its factors are the same thing: 1, negative 1, positive 3, and negative 3. Now, we want to test not these numbers, but we want to test numbers that are made up of the possible p over q's, and both the positives and the negatives of them. So, for example, we could first try to take 1 over 1 right over here, which is, of course, going to be equal to 1. Now, how can we test whether that is actually a root of g? Well, we can just try to evaluate what g of 1 is going to be equal to. G of 1 is going to be equal to 3 times 1 to the third, which is just 3, plus 11 times 1 squared, which is just 11, plus 5 times 1, which is just 5, minus 3. So if I just eyeball it here, these two things cancel out, and I am left with 11 plus 5, which is equal to 16. So 1 is definitely not a 0. If it was, then we would have gotten a 0 here, not a 16. So we can rule that one out. So this is not a root. Now let's try negative 1. And there's a couple of ways we can get negative 1. We could have a negative 1p over a 1q. You could have a positive 1p over a negative 1q. Or you could even have a negative 3p over a 3q. Or you could have a positive 3p over a negative 3q. So those are all ways of getting to negative 1. And so let's see if that's a root. So g of negative 1 is going to be equal to 3. Negative 1 to the third power is negative 1. So this is going to be negative 3 plus negative 1 squared is 1 still. So this is still going to be a positive 11. And then plus 5 times negative 1, which is negative 5. And then we have minus 3. So let's see what happens here. We end up with negative 3 plus 11 is 8. Minus 5 is 3. Minus 3 is equal to 0. So we have found one of our roots. Negative 1, x equals negative 1 is one of our roots. Now, how can we find the other roots? There could be, especially if we're looking at imaginary roots here, there should be 3 of them. So what we can do, if we know negative 1 is a root, then that also tells us that x plus 1 must be a factor. Because if you said x plus 1 equals 0, then you'd get x equals negative 1. And so let's divide x plus 1 into the rest of this polynomial and start to factor it. So if I take x plus 1, and I'm going to do algebraic long division. You could also do synthetic division, but I prefer algebraic long division because it feels a little less mysterious. So x plus 1 goes into 3x to the third plus 11x squared plus 5x minus 3. So you just look at the highest degree terms. X goes into 3x to the third. It goes 3x squared times. So I'll write here in the second degree column, 3x squared times. And all I did is I took 3x to the third divided by x to get that. 3x squared times x is 3x to the third. 3x squared times 1 is plus 3x squared. And this is just like regular long division. It has a lot of similarities. Now we subtract this. That cancels with that. And 11x squared minus 3x squared is 8x squared. Bring down the first degree term, plus 5x. X goes into 8x squared 8x times. If you just take 8x squared divided by x, you get 8x. So 8x times x is 8x squared. 8x times 1 is, so we have plus 8x here. We subtract again, and we get 5x minus 8x is negative 3x. And then bring down this constant term, minus 3. X goes into negative 3x negative 3 times negative 3 times x plus 1 is negative 3x, and then minus 3. And of course, now if you were to subtract this, we get no remainder. That makes sense because we already saw that negative 1 is a root, or that x plus 1 is a factor. So now we could actually rewrite g of x. G of x is equal to x plus 1 times this business, 3x squared plus 8x minus 3. So now this is a standard quadratic. We can try to factor this, or we could use a quadratic formula. I'm going to use the quadratic formula here. So we remember negative b plus or minus. Well, let me just write it out here. So this is our a. Let me just in another color. This is our a, this is our b, and that is our c. So quadratic formula, negative b, so that's negative 8, plus or minus the square root of b squared, so that's 8 squared, so it's 64, minus 4 times a, which is 3, times c, which is negative 3. So I could put a 3 here and then make this positive. And then all of that is going to be over 2a. So 2a is 2 times 3 is 6. So this is going to be the same thing as negative 8 plus or minus 4 times 3 times 3. This is all 36. So under the radical, you have 64 plus 36, which is 100. Square root of 100 is 10. So negative 8 plus or minus 10 over 6. And so this gives us x could be equal to, if we take negative 8 plus 10 over 6, negative 8 plus 10 is 2 over 6 is positive 1/3. Or if we take negative 8 minus 10, that's negative 18 over 6, which is negative 3. So there you have it. We have figured out what our roots are. Our roots are negative 1, that's where we started, and also 1/3 and negative 3. If someone asked you to factor this whole thing, we could now write, maybe I do this in a new color. We could write, I'm running out of space here, but let me just in this white color. G of x is equal to x plus 1 times x minus 1/3 times x plus 3. That would be it in a completely factored form, and we all were able to get there by using that rational root theorem.